Oh, you got it. Is it bouncing? All right, I'll begin. Heavenly Father, we thank you for this day. Thank you for all these students who are interested in this course. And I just pray that you help us use this time wisely, Lord. In your name I pray. Amen. It's good. It's so good to see so many of you here today. It inspires me to want to do it again. Let's see here now. I'm just kidding. What is there any particular one you guys want to talk about?
Yeah, number 16 kind of came up.
Which chapter?
Oh, chapter 2.
Chapter 2, number 16.
Socks, shoes, and
Okay. Yeah, let's work through that. So we're asked to basically show that this is the claim. So this is the so-called socks, shoes formula, right? That in a group we can prove that A times B inverse is equal to B inverse A inverse, right? That's not the whole problem, is it though? Because you're supposed to find an example that shows it's possible to have that doesn't work for
AB.
But they're like AB to the minus 2 is not equal to B to the, I mean, I'll try that kind of, when it's this example finding stuff, it may or may not go well for me. It says find distinct non-identity elements A and B from a non-abelian group with the property that, and then he also wants us to illustrate. So I'm guessing you guys can prove the sock shoes property just fine, right? If I had to guess. But we'll start there, right? It said draw an analogy between the statement. Oh, he says explain the sock shoes label. Okay, great. Thanks, Gallian. Let's see here. Okay, so if A and B, so here's the proof, basically, of the claim. Right? So if A and B are elements of the group, then A inverse and B inverse are in the group, right? Because the group is closed under inverses. And so, and AB is also an element of the group, right? Since it's closed under multiplication, right? So at least the A and B make sense, and also, right, is also an element of the group. It's true. Okay, so fine. I mean, I guess I'm not sure how much of that I actually need, but I guess it's good. All right, so consider then. If we take AB, right, times B inverse A inverse, what do we get? Right, by associativity. And that, of course, is A inverse, right? Where E is the group identity. And of course, that's what? That's A inverse, which is also E, right? So what's this show? Therefore, B inverse A inverse is an inverse for AB, thus AB inverse is equal to B inverse A inverse.
So if the way that you're kind of like a method for other similar proofs.
A method for other similar proofs. Well, I mean, the question is, the claim is saying what? The claim is saying that AB inverse is B inverse A inverse. All right, so Rick, what is being claimed is really the question, right? It's not the right-hand side, because this is just a product of two things. I mean, the thing that's not obvious before this question is, what is the inverse of a product? Now, how do I know that this calculation shows that the inverse of this product is just that? Well, it shows that this right here, this calculation shows that this has the functionality of being the inverse of that by definition. But we proved that was unique on day one. So that has to be the inverse of AB under the inverse operation of the group. As to how typical this is of other problems, I do not know.
I think there was one that sort of asked for the converse.
Yeah. Let's see here. Let's see here. Let me try to get a sense of AB. I'm not sure about the other parts. I may. AB to the minus 2, what's that mean? That's AB inverse times AB inverse by definition, right? Well, I mean, that's just by definition. What was our definition of the negative power? I stated it in class. I mean, I gave you a recursive definition for like g to the n. What did I say g to the minus n was? That's important here for the moment.
Well, I know g to the negative n is equal to g inverse raised to the n power.
Oh, okay. So that's what I did here.
Yeah.
Actually, no. There. Right. Okay. And so we just figured out that AB inverse is B inverse A inverse, right? So what should this be, generally speaking? It should be B inverse, A inverse, B inverse, A inverse. And so if A and B don't commute, I mean, if A and B commute, if it's a commutative group, then you can just switch the order of these. Then we get B inverse squared times A inverse squared. So it seems to me that the not equals is going to come from some non-abelian example. Okay. So I don't know. Yeah, maybe 1, 1, 0, 1 is A, and I don't know. 1, 0, 1, 1 is B. So I'm looking for a counterexample in GL2. I'm lurking in G. When I look for a non-abelian thing, well, after Friday, I might try something else, but at the moment, 2 by 2, you can sit closer if you want. Mostly, it's important to not, I mean, you want to stay on the board, right? Like, if you can see the wall, it's too zoomed out. It won't show up. Yeah. So, what's A inverse here? B inverse is the determinant of both of these is 1. So like the 2 by 2 inverse formula was fast. And then I don't know, what's B inverse A inverse equal to? Excuse me. And so what's B inverse A inverse squared? Square this, we get what? Two. I just have to write it out. I'm an idiot. Fine, so I get the 2, I get the minus 1, minus 2, minus 3. I've probably made a mistake by now. Minus 1, minus 3, 1 plus 5, yeah. So that would be B inverse A inverse squared. And I should compare that to what? Versus B inverse squared, A inverse squared producted, right? I mean, I'm supposed to show that these are not equal in that for the exam, you know. So I'm just looking for an example. I think this will work. I don't know. So what's B inverse squared? One. Minus 2. 0. 1. A inverse squared looks to me like is 1. 0. Minus 2. 1. If these work out to be equal, I'm going to scream. It shouldn't. I think odds are against it. 1. How did I think to do this? Like, what caused me to do this? To look for these counterexamples like this. Like, I know I need a non-abelian group, right? And just the simplest non-abelian, one of the simpler non-abelian groups I can think of is just 2x2 matrices. Or the dihedral groups we'll study tomorrow. But we don't know those yet, so for the moment, this is good. So that and that are obviously not equal, and so there's an example of AB to the minus 2 not being equal to B to the minus 2 times A to the minus 2. In other words, the sock shoes doesn't generalize to put on your socks and take off your socks and shoes 2 times is not the same as taking off your socks 2 times and then taking off your shoes 2 times. But the original one is like, if A times B is like putting on your shoes and then putting on your socks, then the inverse is like taking off your shoes, then taking off your socks. That's the meaning of the socks shoes. Yeah. All right. Well, anyway, I'm going to stop talking about this problem. You guys have other questions about the Z? I'm going to work 27 while you're looking. Number 27 in chapter 2 is a, I don't know if you, I'm not sure I even recommended that, but it's a nice little problem.
26 you recommended.
Oh, okay. Yeah, sure. Actually, that's about the same kind of difficulty. I can look at that one. So you already got all that? Okay. I guess I'll work over here for the moment. So 26, we said?
Yes.
Chapter 2. We're supposed to prove if AB squared is equal to A squared B squared in a group G, then AB is equal to BA. Right? And, you know, this is a slightly sloppy statement. I mean, what he's really saying is if AB squared, or a different way to say it is he's using a custom of language, right? If this is true for all A and B in a group G, I mean, let G be a group, right? Here's a better way to state it. Let G be a group, settled. Then if AB squared is equal to A squared B squared for all A, B, and G, then AB is equal to BA for all A, B, and G. Of course, you don't have to use the same letters. I mean, I could have the same logical statement and have over here X, Y, Y, X, right? Okay. So let's try to prove it. So we assume that assume that a squared b squared is equal to, I'm an idiot. Assume that ab quantity squared is equal to a squared b squared, right? For all a, b, and g. Okay, what does that give us? Let's write out what that means. That means AB times AB is equal to A times B times B, right? For all A and B and G. So what can we do to that?
Oh, we can just multiply A inverse on the left and B inverse on the right.
Right, let's say multiply A inverse on left and B inverse on right to obtain A inverse AB, AB, B inverse equals to A inverse AB, B, B inverse, which of course implies that, I mean, fine, we're starting, I will write steps. So, I mean, we should always write steps. EBA, 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 E. eBay.
There's an A left out.
There's a bay in this problem. What's that?
On the A inverse should be A inverse A, B, B, B inverse.
Oh, thank you. There, better. What? No, wrong side. Sorry.
No, that.
It was this one, wasn't it?
No, that one's fine. The other one's missing an A.
Oh, yes. Sorry. So look, this is like, you can make some stupid meme from this, right? And then we got E, A, B, E. Of course, this implies then thus. And that, of course, is for all A, B, right? Thus, BA is equal to AB for all AB and G. Now, I think my use of for all A, B, and G could be shortcutted. I mean, there's a grammatical construction we could use here to avoid writing for all A, B, and G 13 times in our statement, right? Like, we could just say, consider this, do the algebra, and then have a sentence at the end that says, but the calculation above holds for all A, B in the group, therefore A times B is equal to B times A for all B. Or we could be educated and say, thus G is abelian, which would be even better. Yeah, this one looks scary to start with, right? But then when you expand what it means, it's like, oh, I knew that. I could have done that, right? Next.
What I was going to ask, but I think it actually was part of the assigned homework. Oh yeah, it was. Okay.
I will give you a hint for number 37. Keep in mind that the identity in number 37 is not 1001. In fact, when you work out number 37 carefully, you guys will find that the identity is a half, a half, a half, a half. It's all halves.
Immediately.
So, oh, it's 37. Yeah. That's funny. Any questions from chapter 3? Well, you can just look at it and see if there's any ones you'd like to know there. Okay, I will pick something I like from chapter 3. Here, how about this one's kind of cute. Oh man, that's not the one. Curses.
Sorry, this is
Yeah.
a question back from chapter 2. When we're
That's fine.
trying to prove things or groups, is it fine to just kind of say, like, from things we know from linear algebra, that this has this has an inverse, or like for matrices and stuff?
You are allowed to use linear algebra, usually. If it gets carried away, you'll find out about it, I guess, yeah.
I did, number 34, you're supposed to prove that the matrix of the form.
Yeah.
Matrix. I didn't know how to show it as an inverse.
Just calculate it. You can calculate the inverse of that matrix without much difficulty.
It's gonna last some years.
Yeah, for 34, in terms of finding the inverse, you can just, I think that actually is a subgroup in this case. I could be wrong, but I think that's a subgroup. If it is a subgroup, if it's not a subgroup, well, that's the thing. If it's not a subgroup of GL3, then your linear algebra will not work here. Like the matrix inverse will not be the group inverse, just like in 37. So you'll have to find the inverse directly. In other words, simply calculate GH equals to the identity for a given G. So like another way you can look at 37 is like this. It's really A, B, C star, X, Y, Z equals to stuff, right? This stuff is A plus X. Y plus A Z plus B and C plus C, so C plus Z. I think. I mean, you could look at the Heisenberg group just as sort of formal multiplication on R3.
Okay.
And then the question is, there's a couple different questions. The first question is, what's the identity, right? You need this times E, right? We could say E1, E2, E3, I don't know, what are we going to do? So what does that force the identity to be? Once you figure that out, then you got to solve like this for an arbitrary ABC, and your XYZ should be formulas in terms of the ABC to find the inverse. I think you just have to do algebra. Yeah. That was dangerously close to talking about your homework. Is there another? Maybe too close. Let's see here. So, this one's kind of cute, though. He's got modulo 91, right? You have a group under multiplication mod 91, and it has 1, 9, 16, 22, 53, 74, 79, and 81. And then apparently one thing was missing. He's like, an abstract algebra teacher intended to give a typist a list of 9 integers that form a group under multiplication modulo 91. Instead, one of the 9 integers was inadvertently left out, so the list appeared as above there, which integer is left out. And then he says, this really happened. It's very exciting. I love these questions.
Wait, where is
This is on page 54. I love this. This problem is like so nerdy. So incredibly nerdy. I love it. I love it. Let's see, that's one question. And then the other, let's see here, one that follows it is, if you're given that for every triple in the group you have AB equals to CA, then B equals C, prove the abelian. That's interesting, right? Problem that follows it's interesting, isn't it? You're given that AB equals to CA implies that B equals to C for all A, B, and C in the group. Allegedly, this data right here is enough to imply that G is abelian. I love these little abelian problems. They're funny. So 13 is an odd problem. In the back of the book, he tells us that this is what it is actually. Is this is the group of units of order 91. So the question is which numbers are relatively prime to 91. That was kind of the point of the problem. It's a very yeah, I know, right? Of course, to figure that out, what you could do is you could start taking multiples of these numbers, modulo 91, and see what's missing. So we can figure this out not by thinking directly about the answer, but thinking about products. But I probably need a calculator. I mean, let's see here. For example, 9 times, what's 9 times 22? What do you say? 198? Is that right? What is that mod 91? That's 16 mod 91. So let's see, 2 times 91 is what? 182. Yeah, we should probably keep that in mind. So yeah, you're right. That's congruent to 16. Oh, we already got that one. That's no one help. How about 16 times 16? What's that? 256? 250 what? Is that 256? What's that modulo 91? What's 3 times 91? 273. So if I subtract 273, what do I get? I guess I should subtract 182. I get 474. Oh, that's already on my list. Oh well. Let's see here. But this is kind of, I mean, I could reasonably give you guys a problem like this on the test, right? I give you an incomplete picture of a group. I tell you the rule of the operation. You can figure out the rest of the group by just taking products. Eventually it'll fill out. Let's see here. I don't know. We could be at this a while. It's not that, you get the idea. You just keep taking products. Eventually we'd find out that we're missing. Or maybe you can just see from looking at what's relatively prime, what's missing in the relatively prime list, you know? What was this, number 13? 29 is missing. See, but that's not, it's not at all obvious where that comes from in this list, I mean, product-wise, but that's what's missing. All right, so let's look at the next one, which is probably more interesting. That one's just kind of a, yeah, you can have a scientific calculator and test. All right, so let's see if we can do this one here. So assume, right, that for all A, B, and C in the group, if we have this implication, AB equal to CA implies B equals C, how does that get us abelian? So we do. So let's see here. To start with, assume this, right? So you're like, consider. So what did you say to do? I just didn't hear you. It said set what? Yeah, but you can't just assume what you're trying to prove. I mean, you're just saying assume AB equals BA. That's what we're trying to prove. You can't just say, well, suppose the group's abelian. Oh, it's abelian. What's your starting point again?
Starting with AB equals CA, right? You have that. And then, or you can even just start with AB. And, if you're just working on the left side, then you replace B with C. Then you know that AB equals BC. And then, since you know from above that AB equals CA, then you know that BC equals CA.
I'm not seeing it. But that doesn't mean that you're not right. Let's see here. Which number was this? Number 14. So what should I write down to start with? Oh, CA equals CA? I mean, I have to start with something true.
Yeah, and we're assuming AB equals CA, right? So,
You want to start with CA equals CA?
I think that would get to what you were saying. Like, if you start with CA equals CA, could you, since B equals C, can you say then that CA equals BA?
This implies what?
That CA equals BA since B equals C?
Well, this implies what, though? I mean, this is true. So that implies... You're saying that, I mean, the implication is that the pattern is this equal to that. So you're saying that, okay, so this and that match, right? So that implies A equals to C, right? That's using, I mean, that's using the data at least, yeah?
Oh.
No? Does it help if I write it AB equals to AB? So I have that AB equals to...
okay.
Wait a minute, but I can't do that. I'm sorry, I can't do that at all, because I need A over here. Yeah, I'm sorry, you guys fished me in for a second there.
But we're assuming AB equals CA, right? So let me start with that.
I don't know what that means. I mean, you say you're assuming AB equals CA. What do you mean?
We're assuming that, and we're trying to prove that implies that G is Gallian, right?
No. You are assuming that you have this implication, which is that if you have this equality, it implies that equality. Using this data, you have to show that AB equals to BA for all AB.
That's what I was understanding.
Okay.
What we were trying to prove is that if we do it based on that assumption that...
the data we get is this implication, you know?
So we're trying to show that AB equals CA implies that B equals C.
Mm-hmm.
That's what we're trying to show? Okay.
No, we're trying to show that
That assumption.
implies A equals B.
Right. Right. So I need an A on both sides somehow, right? Like, what if I do ABBA equals ABBA? Is that helpful? Not quite, because yeah.
If you take the A off, we know that A equals B by the assumption.
I suspect this might be like a contrapositive problem. You know? Maybe this is a contradiction problem. So suppose AB is not equal to BA. I mean, suppose there exists, right? Right, that's the contradiction of abelian. If there exists a pair that doesn't commute. I don't know. Honestly, guys, I'm not sure how to do this one at the moment. I mean, that's what I was thinking, but I don't know. I'm a little lost at the moment. I'm not sure which way to go. I doubt it's anything terribly complicated. Yep.
Can you do AB equal AB?
AB equals to AB. Okay.
Then ABA equals to ABA.
ABA equals to ABA. Okay.
Then parentheses ABA parentheses AB parentheses A.
Like this.
So BA equals.
So you're identifying this as the quote-unquote B, and you're identifying that as the quote-unquote C. Excellent. That's exactly it. So this implies that BA is equal to AB. Yay! Yeah, that is it. Thank you. Phew, it's a good thing you came today. Otherwise, I'd be silly when somebody emailed me that later. I'm like, oh, so sad. I'm still a little bit sad I didn't think of it, but there it is. Do you see how that, I mean, so he's using the assumption, making that appropriate identification of the B and the C up here, right?
I think I understand.
Yeah, I mean, it's even easier if we do something like X, Y, right? That implies X equals to Y. So then you can say, okay, so that's my X and this is my Y in the assumption. Okay. All right. Let's see here. Chapter 3, let me try to pick one.
There are two that they left up to the reader in the reading maybe or something.
Yeah, I'll probably, I might do the proof of the CA as a subgroup tomorrow. I don't know, I'm thinking about it. Depends on, let's see here. Trying to find something. I gotta keep an eye on the time. If I go too late here, I'll get in trouble. Mwahaha. So I got 5 minutes. I gotta find a 5-minute problem here. This one's kind of fun. This one, I won't get stuck on this one. But you guys probably don't need me to see me do this one either. Let me try to do 34. U15 has 6 cyclic subgroups. Now, we haven't talked about that yet in lecture, but I will very soon tell you what a cyclic subgroup is. So, you know, we talked about subgroups last time. A cyclic subgroup in a multiplicative group is something like this. You take an element A, and then the group is formed by A squared, A cubed, dot, 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 dot. Eventually you get to A to the n equal to E, and you're done. So U15, what is U15? The group of units, mod 15. So you got yourself a 1, a 2, 4, no 5, no 6, 7, 8, no 9, no 10, 11, 13, 14, there it is. So this is done multiplication mod 15, right? So here, for example, if we take 2, subgroup generated by 2, cyclic subgroup generated by 2, that's basically just 2 squared, 2 cubed, 2 to the 4th, and so forth. I'm not sure how big that is. But basically the question is, what's the order of 2? As we talked about last time. In other words, what's the smallest integer power that when you raise it, you get back to the identity, which in this case is 1. 2 to the 4th is the deal. 2 to the 4th is 16, which is 1. So this is going to be 2, 4, 8, 1.
And 2 is called the generator.
Yeah, 2 is the generator. Let's see here. What happens if we use 4? We get 4, and then we get 16, but that's really just 4 and 1, right? And I'm sorry, I really shouldn't use this here. I should use curly brackets. My bad.
So,
The angle bracket has a technical meaning that's what this angle bracket means to do this in the multiplicative context. These are subgroups of U15.
so does 1 not count as a slip?
Oh, yeah, we can do that.
Is it just infinite?
Just 1.
Oh, just
Yeah, the order, I was quibbling.
gets back to
Yesterday I was like, he's like, what's the order of the identity? And I was like, I don't know. I'm like, I should just told him 1. The order of the identity is 1. Because the order of an element should be the order of the subgroup which it generates. The order of 2 is 4. It generates a subgroup of order 4. The order of 4 is 2. It generates a cyclic subgroup of order 2.
Is that something that has to be proved, or is that just kind of true? The order of an element is the order of the subgroup.
That's something I suppose we could prove. Let's see here. But it's true. All right, so let's see here. 7. What do we got? You got yourself a 7. 7 times 7. 49. So yeah, 4 times 7 is what? It's 28, which is minus 2. See, when you're doing modular arithmetic, there's like 2 different ways to go, right? And one of the ways you can go is like this. And sometimes like that makes calculations easier. That says that I have to go pretty soon.
So negative 2 times 7 is negative 14, so I guess it's back to 1.
Oh, really? Negative 2 times 7 is negative, what is it?
Negative 14.
Negative 14, which is 1, right? Very good. So I don't know. I'm not sure. I'm not totally sold on negative calculations. Anyway, this is really what? 13, right? Yeah. So there's a cyclic group of order 4. And if you keep doing this, right, with these things, you'll find that you get 6 cyclic subgroups. Apparently, as you go up this list, they're not all going to be distinct. Something in here is going to be something we already found. Now so far we found distinct ones, but they're going to be 6 different ones. It turns out, for some of the subgroups, there are different generators. There are 2 different generators which will generate the same subgroup, and yet be different somehow. I guess that happens. But it'll have to remain a mystery because I must go. You can hit the record.